what we're going to start talking about today is something called a sampling distribution. So the idea here is that you want to take samples and make conclusions about populations, right? That's a big idea. And the question is how much are your samples going to vary? Like in the presidential election where they're doing polls to try to figure out who is going to win, they want to know, well, okay, I have this sample, and then how likely is it that a different sample would look different, or that would be the same as mine? So that's kind of what we're going to talk about, is how if you take repeated samples of the same size, how those samples might vary. Okay, so one of the main applications of statistical methods is to use blank data to draw conclusions about blank. So we already said that. So we're going to use sample data to draw conclusions about who? Populations, exactly. And one big reason for that is it's not really feasible to always look at the population, because that would involve doing a census, big, complicated, messy, ugly, etc., right? Okay. So we need to know how to make use of sample data to answer questions about the larger group of individuals, and we're going to study the reasoning that lets us reach conclusions about an entire population on the basis of a small sample. So in general, you're going to follow these steps. So start by posing a question about a population. So for example, what proportion of students pass Stat 200 at UAF? Like, what is the true pass rate? Like 70%, 60%? Does that make sense? It's a question about a population. A sample could be like your class, right? Sample of 60, what is your pass rate? Could estimate that, right? And I could use my data from the first time I taught this class to do it as well. So that would be you're collecting a sample from the population and measuring the variable of interest. So, like I could compute the pass rate for, if I want to do it now, F 2015, like fall 2015 when I taught this class before. And then I could use that estimate to answer my question about the sample. Now, is it likely that my pass rate this semester is going to be the exact same as the pass rate from fall of 2015? No, because it could be that hopefully I try to get better and so explain stuff better to you guys than I did to them, those poor students. Also, hopefully you guys do better. I don't know, maybe you're... Yeah, I did. But this year I'm going to take attendance the entire way through, which I didn't do last fall. So maybe that'll have an effect. So anyway, the point is that different samples are going to give you different estimates. Okay, and even if you kept the conditions the same, if nothing had changed, they're probably going to give you different estimates because people are vary, right? And then using statistical theory, you can determine how close the sample answer is to the true answer for the population. So that's kind of what we're going to do basically for almost the rest of the semester. I think Chapter 7 is the hardest, and this is not quite as hard, but it's not as easy as Chapters 2, 3, and 4, okay? We're not going to go back there.
The next exam will be mostly Chapter 9.
The next exam is going to be approximately even 7, 8, 9. A third, a third, a third. But it'll be like stuff that's on your quiz, and we'll review, so it'll be fun.
Take a 2/3 in the exam because that's probability section.
You're going to have to figure it out, at least some of it. Okay, a blank or blank is a number that is a summary characteristic of a population. What was the word for this? Kind of review.
Oh,
It starts with a P as well. It's okay.
proportion.
Parameter.
Parameter.
There we go. Parameter. A proportion is a specific kind of
I knew
parameter.
it wasn't.
Or sometimes people call this a population parameter. Good, there's alliteration there. You can do poetry in math class. PP. It's a summary characteristic of population, random situation, or comparison of populations. Now, the parameter is something that's true for the entire population, which you really can't measure, but you assume that this is a fixed or unchanging value. We could say, okay, for today, there is a fixed number of people who are going to vote for candidate X. And I mean, it might change tomorrow, but today's proportion parameter is fixed. To do a census today to figure that out, we're not going to do that. Okay, and then a blank is for samples. Remember what that one is? A statistic, great. Statistic or a sample statistic is a number computed from a set of sample values taken from a larger population. It's a numerical summary of the sample data, so it could be a proportion. It could be a mean. Like the proportion would be like the proportion of you who passed Calc 1. Or, sorry, you're not in Calc 1, statistics. And the mean could be like, okay, what is the average height of people in my statistics class, right? I mean, like, why would I care? I don't know, but that'd be an example of a mean.
See if height has something to do with something you pass away on.
To see if statistics students are taller on average than the rest of UAF. I don't know. Okay, something like that. And so now, if I repeatedly compute sample statistics, are they always going to be the same? No, these things are going to be variable, as in they change. And will be probably different from one sample to the next. So parameters don't change, statistics do. And a question you want to ask yourself is, how much is that statistic going to vary if I repeatedly do samples of the same size and compute the same proportion? Okay, so in each situation, explain whether the given value in bold is a statistic or a parameter. So a polling organization samples 1,000 adults nationwide. Sorry, that should say nationwide. And it finds that 72% of those sampled favor tougher penalties for persons convicted of drunk driving. So is it statistic or parameter? Statistic. Right, when you see the words U.S. Census Bureau, you can pretty much automatically say this is it's a population parameter. We should read the rest though, just because. It found the median age of, and the kicker really there is all American citizens, was about 35 years.
So what if it was something to do with like the whole world, then it would be.
Yes, exactly. But since it is the U.S. Census Bureau, then the population you're looking at is the U.S. and not the entire world.
We're still like a decently young country.
And I haven't gone over that age yet. Yes. Okay, a writer wants to know how many typing mistakes there are in his manuscript. So he hires a proofreader who reads the entire manuscript and finds 15 errors. That's a parameter because the whole manuscript was read.
It's pretty good for a whole manuscript.
Right? Well, it depends on how long the manuscript is, right? That certainly isn't true for my note sheets.
It's like a child's book.
Here, let me read this kid's book and find how many errors you have. Exactly. Okay, so that part's pretty easy. Now, the results in this unit are going to be used for the rest of the course, and they make conclusions about parameters. Parameters on the basis of the estimates of those parameters, which are statistics. So you can think about parameters as true values based on what you see in a sample. And the procedures that are used for making these conclusions are called statistical inference procedures. As in, you're going to infer that, oh, this statistic is actually different than my parameter. And I didn't tell you that yet, but you kind of have already done these. Done 2 baby examples of each of them. The first one was in chapter 4, when we talked about null hypotheses, and are these two things different than each other? Like, is the proportion of people who get divorced and smoke different than those who don't smoke? And does that make sense? So we did that in chapter 4. That was called hypothesis testing. That was chapter 4. And we did a very specific case. We're going to talk about more general cases as well. And we also did a little bit with confidence intervals, right? Remember that? Confidence intervals. That was chapter 5. And that's where we use that 1 over root n formula to get the margin of error. Remember that? Okay. But what we're going to do in chapters 10, 11, 12, and 13 is do this more generally. We just did confidence intervals for proportions, as what proportion of you are going to pass statistics. But you can also do confidence intervals for for means, so like what is the average body temperature? Like how much does that vary? And that's not a proportion anymore, because proportions are between 0 and 1, right? Proportion percent, right? Okay. Okay. So a confidence interval is an interval of values that the researcher is fairly certain is going to cover the true unknown value of the parameter. As in, you're pretty sure that that sample contains the actual parameter. So in other words, you use the confidence interval to estimate the value of a population parameter, as in, like, it's within a certain range. You say, I'm pretty sure it's between this value and that value. So, for example, vote for candidate X and you get the confidence interval is like 0.53 to 0.56. You're pretty sure the actual proportion is in between 53 and 56%, right? Okay. Hypothesis testing or significance testing uses sample data in an attempt to, what with the hypothesis? What are you trying to do with that? Usually with hypothesis testing, reject or accept?
Confirm?
You're trying to, but usually you kind of go about it a little backwards way, don't you?
Yeah,
Usually you go about it by trying to reject the hypothesis. You say, I think this thing is true, and then you say, oh my gosh, it's so unlikely that just can't be possible. So the goal with hypothesis testing often is to reject your null hypothesis. You never, ever, ever accept H naught. I think I told you guys that, right? That you never accept H naught. You just fail to reject it. And usually the researchers, you want to reject the notion that chance alone can explain the sample results. So your goal with hypothesis testing often is to reject H naught. Let's add that in. So the goal is to reject H naught. And what we did in chapter 4 was about population proportions. We're going to change our focus, at least to start, to test hypotheses about population parameters. So, for example, is the body temperature that's normal actually 98.6? Like, is that actually average body temperature? I think it's actually 98.2 or something, right?
It was 97
A
something.
couple people are in the 97.
Yeah, so where is the actual mean, right? That's one thing we'll test that little thing about. And to do this, you have to assign something called a null value for the parameter. Now, it's unfortunate that English isn't like German or Swedish or Russian, because in all of those languages, anybody know what null means in those languages? Zero. So the null value doesn't necessarily mean it's zero, it just means no change. So whatever thing is like the status quo is your null value. So for example, in a weight loss clinic, if you're trying to figure out if their methods are effective, the null value would be, no change would correspond to how many pounds lost? Zero. And they would like to show that their weight change of 10 pounds is actually different than zero, right? If you're testing if average body temperature is really 98.6, what's the null value for that? 98.6, obviously not 0 degrees, right? Okay.
Now I'm going to put that on the test because
Yeah, exactly. In most cases, researchers hope to show the null value is correct or not correct. Is not correct. And if they show it's not correct, what can they do with the null hypothesis? They can reject it. And we will actually go back to that example about body temperature, and we'll actually reject that. Okay, that is not the right value. It should be lower. Okay, and when you perform a hypothesis test, I'll turn my notes over. First, you obtain a sample. Then you compute a statistic. And you assess how likely this value is if the null parameter is true. And the phrase statistically significant is used when the sample statistic would not be likely if the null hypothesis were correct. If you're statistically significant, what does that mean about H naught? Reject or do not reject? Statistically significant means you reject H naught. Those two things are synonymous. Because you reject H naught when your p-value is low, which means unlikely due to chance. Okay, so for example, for body temperature, I could take all of your temperatures. Of course, not when the room is super hot, because that might skew things, and test if the average temperature I get from you guys is different from 8.6. That'd be a way to do, test that thing. Okay. So a report in Newsweek about the relationship among diet, genes, and disease discussed the E4 allele for a protein known as APOE and said that an estimated 15 to 30% of the population has at least one copy of the allele. People who have this allele are at a higher risk for diabetes, heart disease, and Alzheimer's disease. So what is the population parameter of interest in the quote? What do they care about? Not just the people, but the proportion of people that have the allele. Does that make sense? Okay, so the proportion of the population that has the allele. And how do I know to use the word, and just quickly, proportion means percentage, right? So proportions are going to be between either 0 and 100%, or what as just 0 to 1. Okay. Would it make more sense to find a confidence interval for this population parameter, or would it be better to conduct a hypothesis test? So here's how you can think about this. Use a confidence interval if you don't have any idea what the true population proportion is. Does that make sense? And you use a hypothesis test if you think you know what it is but want to know if that's right. Does that make sense? So for body temperature, we think it's 98.6 if we use a hypothesis test, right? But for this one, do we know what proportion of people have this allele, at least? No. So a confidence interval gives you a range that might contain the actual thing. And in general, actually, I've read some books about statistics done badly, and confidence intervals are actually almost always better because seeing a range of values is more meaningful than, oh, this one is wrong, for lots of stuff. But for this one specifically, not knowing what a null value would be, you would say population, you'd say confidence interval. So we'll say confidence interval. And there's no obvious guess for what would be a null value. And you need a null value for a hypothesis test. And then also the confidence interval, which I'm going to abbreviate CI. This gives a range of possible values. Which I really think is more useful, don't you agree?
Yes.
I think so.
It's easier on the brain to look at a specific value.
Yeah, I think it is easier to conceptualize that, 15 to 20% as opposed to just not 20% or something like that, right? I think it's easier and also there will be variability. So it also gives you an example of how close they actually know to the true thing, right? As in the fact that that's kind of wide means that they kind of have no clue a little bit, right?
Rather than 15 to 17.
Exactly, which is much, much, much more tight. So it gives you an example. And usually larger samples produce smaller intervals. So, that might be because they had a small sample that they tested. So the phrase an estimated 15 to 30% indicates that the scientists don't know precisely what percentage of the population has the allele and explain why they don't know. So they don't know exactly because what did they get this from? A statistic or a sample, right? And so they didn't actually do, that's why they don't know for sure. So the scientists couldn't measure, so the data that made this interval is from a statistic, or from a, we'll say from a sample. The only way to know the true value is to test everyone. And in this case, that's not possible because it's probably too expensive to get everybody's genetic test, right? That's not going to actually work. Is that idea okay? Yeah, ish. All right. All right, so that in a general nutshell is section 9.1. This is not that bad. It's just what's the difference between parameters and statistics, and, you know, that's really not that hard. Okay, one of the most important skills a good researcher needs is the ability to translate curiosity about something into a question that can be answered using statistics. So usually you're going to form a question about a parameter. And there are kind of like what this book calls 5 different parameters that come up repeatedly, and they each have different distributions for which you find standard deviations and stuff. Like, I know some of you have actually looked at t-tests before. Anybody seen a t-test? Like, I know you have. And we're going to talk about those tests and why they work and things like that. It's kind of cool. Okay, so for we have 2 different categories. You've got categorical variables, and then we have quantitative variables. And for categorical variables, you can figure out what proportion of people are in various categories. Does that make sense? So the first thing is if you have one population proportion. The parameter is a fixed, unchanging value, and it has specific notation. It's represented by P. And the sample statistic, remember, that thing changes, right? From sample to sample, there's variable. And the way you represent that is you do P with a little hat on top. We saw that notation before, right? With regression lines, you did Y with a hat. And that's because if you recomputed the regression line with different data, you get a little bit different regression line, because your data is used to make the regression line. Okay, now you could also care about difference in 2 population proportions, like what's the difference between men and women, right? So in this first case, let's note one thing. P is going to be between 0 and 1, right? If you have one proportion, and also it could be equal to, yes? But it's a proportion, i.e. percentage, right, between 0 and 1. The difference in 2 population proportions, that would be P1 minus P2. So that's for the actual parameter. And the notation for the sample statistic, what do you think it is?
P hat 1 minus P2.
P1 hat minus P2 hat. So for example, suppose that P1 was the proportion of men who pass stat 200, and suppose P2 was the proportion of women you might want to ask yourself, are those 2 populations different? Like, do women pass more often than men, or vice versa? Does that make sense? So in this case, if you subtract 2 population proportions, when would you observe no difference? If the difference is 0. And if I don't specify putting the bigger one first, what would the range of values be? The range of values is going to be -1 less than or equal to P1 minus P2 less than or equal to 1. because P1 and P2 can go between 0 and 1, right? So their difference could be negative. That'll happen if P2 is bigger, right? I can move it up if people are having trouble seeing, but the point is, with categorical data, you're looking at proportions. Can I go to quantitative stuff now? Okay. So for quantitative variables, we're going to look at means. So the basic situation is one population mean. Okay, what was the fancy Greek letter we used for mean? Mu.
I love that word.
Yeah, it sounds like a cat, doesn't it?
Ew, so cute.
So cute. And what do we use to estimate a population mean? An average. What was our symbol for average?
An O with a tail.
That's the
That's
standard
the wrong one, that's the
deviation.
wrong one.
X almost,
O with a line on top.
X with a line on top, X bar. Remember that? X bar is the traditional average, or maybe weighted average in some cases. So an example for that would be, is mu really 98.6, right? That idea of body temperature, again. Okay, and then the last two are they're a little bit easy to confuse if you don't think. So you could have a population mean of paired differences and then difference in two population means. So in this case, we'll talk about how they're different in just a moment. The population parameter is mu sub d. And the sample statistic is something that your book at least calls d bar. Okay, now what do you think the paired thing means in this? We talked about a little bit about matched pair design, where like putting pairs together. Mm-hmm. Also, you use this when there is an obvious pairing. So, for example, suppose you have weight before you start a diet and then weight after. Like you have two measurements for a person. Does that make sense? And there's an obvious pairing. You wanted to compare this person's weight before to this person's weight after. You compute that difference and then you find the average. Does that make sense?
Would that be used if you were like trying to see on average how much how much people were losing weight?
Yeah.
Like this guy started at this and ended at that, so that's what he lost.
Exactly. Yep. Mm-hmm. You could do the before minus the after. There's an obvious pairing that this person matched with this person. Or another example your book gives is the difference between the height of husbands and wives. There's an obvious pairing that you have husband paired with wife. Or you could do brothers and sisters, assuming you have a brother and a sister in a household. You can compare this brother to that sister. And there's an obvious pairing, and leave out people that only have girls or boys in their family, or only one kid. But the point is you can match the data and you can pair them. Versus the difference in two population means. In this case, the parameter is mu1 minus mu2. And the sample statistic is x1 bar minus x2 bar. And the kicker with this one is that these two samples are separate / independent and not coupled in any way. Okay, so let's think. I didn't write an example down, and I really should have. Here's one. Average age of students at UAF versus the average age of students at the school where I went to school, which is Gustavus Adolphus College, which they called GAC. GAC was much more fun to say than UAF, guys.
Yup.
GAC. Yuff. GAC. Okay.
It's like,
But the point is that the students at UAF are not related to the students at my other college, right? And they're two separate things. We want to compare how are they different. But the paired differences means that there's obviously a pairing. You can match them up. And also, like, this first one means you have to have the same sample sizes. Does that make sense? Whereas this one, they could be totally different sample sizes. Like the college I went to in Minnesota had like 2,000 people there, maybe 2.5. UAF has more than that officially, if you count all the graduate students and stuff.
So the population mean of paired differences has to be the same, like 2 people or 5 people or something?
Yeah, you have to have, like, people have to have a matching pair. And the difference is that you'll find their difference and then find the mean.
And the bottom one, we're just.
The bottom one, there's 2 different groups.
Doesn't matter.
Yep, 2 different groups. It should be, so just when you're looking at the difference between these is there a pairing or are they 2 different groups? And that's what you're looking for. Paired, separate groups. And it should be pretty obvious. Like most of them, I think, is pretty obvious if you just think about it from the samples that you'll be given. Okay, so first of all, explain whether p hat or p is the correct statistical notation for each proportion described. So the proportion that smokes in a randomly selected sample of n equals 300 students. So is that a hat or is that a p?
Yeah.
That's a p hat. Because it's a sample statistic, right? Or it would be a sample statistic if you actually knew the numbers they gave you. The proportion that smokes among all students in the 11th and 12th grades in the US, that should be P. P because from population.
Could we assume that anytime the word all is used?
Yes.
Okay.
Anytime they're using the word all, the book is trying to get you to understand that, yes, we're talking about a proportion. Yep. Because it does matter what you consider to be your quote-unquote world, right? I mean, like if you consider the U.S. to be your world, then population is the U.S. population. If you consider the world to be your world, well, then all of a sudden not, right? Okay. So a student doing a project for a statistics class wants to estimate the difference between the mean number of music CDs, this book is obviously dated, owned by male and female students. He surveys 50 male students and 45 female students about the number of CDs they own. The mean number for the males is 110, and the mean number for the females is 90. Okay, this is obviously dated, like back when I was in college, guys, people still had CDs and iTunes was new. I was in college when the first iPod came out.
110 CDs.
Okay, so that makes me old.
With the buttons on top?
Yeah, it had like the little swivel thing in the middle. Yeah, and it was huge.
Yeah.
I also got one of the first Nanos, which was like a big deal. Anyhow, moving on. Okay, so what is the research question of interest? So what do you think they care about?
Males.
On average, who
have
has more
CDs.
CDs?
Yeah, or like what is the difference, right? So the question is, what is the difference between the mean number of CDs owned in these 2 populations? So what is the difference between, I think I just spelled between wrong, which is terrible, and oh, it's not gonna let me erase. Scribble, scribble, scribble. Between the mean number of CDs owned by male and female students. Okay. Nothing suggested that they suspected that males owned more. Does that make sense? Like, unless they were looking for unless there's obvious statement that that in the problem that the question specifies a direction, just don't assume there is a direction. Does that make sense? Even though the sample gave us that, maybe you just didn't know which way it was going to go. Okay, what is the population parameter and what's the appropriate statistical notation? So, in this case, is there an obvious pairing or are they 2 separate groups?
2 separate.
They're 2 separate groups. So this is the difference in 2 population means. And the notation is mu1 minus mu2. mu2.
How did I say mutual?
Oh, I was making a couple more jokes, but
Population mean of
I got
Shut it down.
And you can say, you know, the men are, the mu1 is the average number of CDs owned by men. Gesundheit. Population mean number CDs owned by women. I don't think we're going to make you be super specific, but what I'm really going to look for is, do you understand that it's two different means as opposed to mu sub d? Was it pretty obvious that they were separate populations?
Yeah.
Yeah, okay.
I think the wording of the question was what got me at first, but then when she said the answer, it's like, oh.
Yeah. So the population parameter like refers to the name and then the proper statistical sim.
So,
Yes.
wouldn't it, just because there's like 50 males and 45 females, maybe I don't understand why it's a difference in two populations. Because
It's
there's 50 men and 45 women, right?
that's part of it, as in the part of it, even if they were the same sample sizes, there's no reason to pair one male with one female. Does that make sense? So since there's no reason to pair them, you're just comparing the average of one group to the average of the other. And if I think it's just best to think with pairs, there's an obvious reason to pair them, like their husband-wife. There's a before and after measurement. That's where you do obvious pairing. What is the value of the sample estimate or statistic? So in the previous one, I said that x1, mu1 was the men. So the sample estimate, so the notation for that would be x1 bar minus x2 bar. As in, that's the x1 is the mean for the number the males own, and x2 is the mean for the number of CDs the females own, which they gave you was, so 20. And I think, just to be consistent and not make your grader's life like a living nightmare, let x1 or mu1 always be the first thing you're talking about. Does that make sense? Like in this one, they talk about the male students first. Just let x1 bar come from that population. Does that make sense? So just be a little bit logical about it. Yeah, I mean, there's no reason it has to go in this order. It's just that it's easier on her if you're consistent. Okay, great. So that paired data is definitely like a little bit hard to reason through. So tell me if this would be independent samples or paired data. So population mean of paired differences, or is it the difference in two population means? So in this one, yeah, what is the average age difference between husbands and wives? That would be paired data, yep. So say paired data, or you could say mean of paired differences. The kicker word there is that it's paired. There's an obvious way to match something to something else. Okay. What is the average difference in ages at which teachers and plumbers retire? Is there any obvious pairing this teacher to that plumber? No, so that is independent samples. Or you would say the difference in two population means. So there's no obvious pairing. How about this one? What is the difference in average salaries for high school graduates and college graduates? Do you pair, but you have to have a high schooler to pair to a college person.
You pair a high schooler and a college graduate.
You pair one high school graduate with one college graduate? I think it's separate. They're totally separate. I mean, you have the group of people who graduated from high school and those that graduated from college, and they're separate groups. So in this case, this really is independent samples as well.
I was gonna say match people's ages, and then I realized that's stupid.
Yeah, because they're going to be different ages.
Yeah.
So they're separate independent groups. Okay. So the big question we want to get to is if we use statistics to make estimates of like the mean of a population, or if we estimate the population proportion, how much is that going to change based on like our sample size? So think of think of taking a random sample as one big random circumstance. So suppose you survey 1,000 adults to figure out who they're going to vote for in an election. And in your survey, you find that 40% are going to vote for candidate A and 60% are for candidate B. You can then repeat this idea with another sample of 1,000 people and do the survey again. Are you going to get the same proportions on the second time? No, probably not, right? But suppose you do 1,000 people again, you're probably going to be different than the first sample. And you could imagine like repeatedly doing this over and over and over with the same sample size, right? Does that idea make sense? And then you can look and see how over time, how when I repeat this experiment, how much does the proportion that I get vary from one to the next. And so the sampling distribution for a statistic is the probability distribution of possible values of the statistic for repeated samples, and one kicker is of the same size. So it'll tell you how much variability you expect if you repeatedly take samples of the same size from the same population. And that will let you determine if your if your sample that you got is sort of special or not. Is it really different? But the idea is you repeatedly do the same experiment over and over, how much will this vary? And how much will it vary is based on a couple things like the sample size. Big sample size, less variation, right? Small sample size, lots of variation. Okay. No, go ahead, it's fine, I've got time.
Always work out without running out my question here makes sense.
They're
You
not,
did the same type of sample, like 1,000 and like 100,000, and you did 1,000 a couple times and 100,000 times. Would it all equate or not really?
not really, so you're kind of comparing samples of 1,000 and samples of 1,000, and samples of 100,000, samples of 100,000. So those are two separate things. So the distributions depend on what the sample size is, and if you take bigger sample sizes, you're going to have less variability. Kind of, I think we mentioned that we talked about how bigger ends made those confidence intervals smaller, right? Less variability in what your estimate was. Same kind of idea. So consider a situation in which a sample of 100 SAT scores is taken from a population of all people who took the test in a given year. What's going to be more spread out? The sampling distribution of the sample means, or a histogram of the 100 SAT scores? Okay, so the idea here is that if you were to plot out where those 100 SAT scores landed, what does the SAT range between, guys? I don't know.
Oh man, what are they each 500 now? Yeah.
I don't remember.
I think it's 32.
The new SAT is up to 1,400, but the old one was 1,600.
But that was together, so what is it, like 0 to 800? Can you get a 0 on it?
0 to 800
Yeah.
when we took the SAT.
When you do them separately, right?
It's different now.
But we'll pretend, okay?
It's different.
It's different now, okay? So you have the scores for all people are going to range between 0 and that, and probably, so that's for each individual score. Like that's your 100 people are going to range within that value. What happens when you take averages? Like if you had a sample of 100 and you take an average, it kind of like pulls it to the middle. Does that make sense? So if you do sample means crap. This I drew this should be this arrow. Drew it the wrong way. Sorry. Erase. Okay. Now, if you look at sample means, as in you repeatedly take 100 people and compute the average score, the average is going to fall in the middle, but it's going to be a lot narrower, and it's going to be super unlikely that you pick a sample of 100 people where people all score super, super low. Like, it's possible, but it's unlikely. But But the idea is that if you find means, and then you look at how are these means going to vary, they're going to have the mean in the same place, and that averaging those hundreds pulls them towards the middle. Does that kind of make sense? So who's going to be narrower or more spread out? Is your sample more spread out, or the sample of samples?
Or your sample.
Your sample's more spread out, but the other thing is like repeatedly sampling your samples. So the histogram of 100 is more spread out. Than the sampling distribution. I don't know why your book doesn't use these words, but another way to say that is that the histogram has a larger standard deviation. Does that make sense? Histogram has a bigger standard deviation. Standard deviation. Okay. And this stuff is going to go back to the normal tables and things that we used, because if you take big enough samples and do repeated iterations of things, you end up with normal distributions. So that's what this next stuff says. So for every single one of those 5 sampling distributions we talked about, the parameters, the difference in parameters, the means, the paired differences, and the difference in 2 population means, as long as certain conditions are met, and the conditions usually are that you have a big enough sample, that sampling distribution that you have is approximately normal. And the sampling distribution is a little bit tricky, but what it's looking at is how much are samples of this given size going to vary. Okay, so the mean of the sampling distribution is the population parameter that corresponds to the sample statistic. So the mean of the sampling distribution is the parameter that you want to know, and it's estimated by your statistic. And the standard deviation of a sampling distribution measures how the values of that sample statistic vary across different samples. And I probably should have said of the same size from the same population. So it's saying how much variation would you expect in samples of this size if we did this experiment repeatedly? When talking about sample statistics, we want to know how much we can expect this statistic to vary over different samples of the same size. And you this is a little bit, it's weird, but what you do is you find a standard deviation of your sample of samples. Okay? So, suppose you have samples of, I don't know, n equals 20. Lots of samples of n equals 20. Then you figure out what is the standard, and you find the mean for all samples. The means are going to vary and be different for every single sample, right? Does that idea make sense? And you figure out then what is the standard deviation for this. I've got all these different means, and what is their standard deviation? So it's a standard deviation of a sample already. You kind of do standard deviation twice. So the standard deviation of a sample mean is called like the standard deviation of x bar. The standard deviation of parameter p is the standard deviation of p hat. Okay, and sometimes, to make it clear we're talking about a standard deviation of a statistic, we use the term standard error. Okay. So suppose you have a situation in which researchers measure a random sample of 50 newborn babies and the average weight is calculated. If a random new sample of 50 newborns is taken from the same population, explain whether the following would change. So is the population mean going to change from sample to sample?
No.
No, this one is fixed. How about X bar? Yes. And C and D, I think, is tricky, but I think I should tell you what's what. So the standard deviation of X bar, this is the true value. Of how your sample statistic varies. Statistic varies. So this is unchanging. So in this case, no. And for X bar specifically, the formula for this is going to be sigma over n. But we'll learn more about that, I think, on Friday's lesson is where that lands. And sigma is kind of like mu. Sigma is the true population standard deviation, right? And n is your sample size, and you assume n is always the same, right? So that's why this one doesn't change. The standard error, this is the estimate of the thing in part C. And you find that in this case using X bar over n. So standard error refers to an estimate of the standard deviation of X bar. And so because this formula uses X bar, it would be changing because X bar is changing. Does that make sense? X bar is different from sample to sample, right? So if you recompute the standard error, it's going to be different from sample to sample. But the true value is this, and that doesn't change. So just if they say the words standard deviation of X bar, that's the true value. Standard error of X bar is the estimated value. So yes, will change. And this last thing, the sampling distribution, this is the description of like how X bar will vary over samples of that given size. So that's kind of like the overarching curve or bell-shaped curve that gives you the possible values of X bars in your sample size. That's unchanging as well. This is like if you could have possibly done infinite samples, what would the curve that come out be? And so that's why it's unchanging, because kind of like if you'd done infinite samples, this is what would come out. So that's also unchanging. Okay, well, 5 minutes to spare, and I guess we can let you have 5 minutes early.